Okay, so today we're talking about static filter data structures. Alrighty. So, so I asked all of you to do some background on what Bloom filters are. Who of you at this point knows what a Bloom filter is? Okay, that's most of you. That's good. So I'm just going to kind of run through the basic Bloom filter stuff, although we'll still do it completely. And hopefully not too long, we'll get to some new stuff. But we'll start with the basics. We'll just do it quickly. Okay, what is a filter? All right, so a filter is this compact data structure that provides an approximate representation for keys in a set. You can ask it whether a given key exists. All right, and the filter will tell you true if a key exists, but if a key does not exist, you might get a true or a false positive. All right, and you'll get a false positive with a given probability. Okay, why do we use filters in systems? All right, so typically in systems, we're dealing with large amounts of data, and this data spans different levels of the memory hierarchy. And we might want to go to a slower level of the memory hierarchy and ask whether a key over there exists. Filters help us, so because a filter is smaller than the actual set that it represents, we can put it at a higher level of the memory hierarchy and then check whether a given key exists without actually searching the data, say in storage or over a network. Okay, now if a given key exists, we're guaranteed to always get a true positive. But if the key that we're querying for does not actually exist, then we might get a false positive or a true negative. And crucially, we get a false positive with a probability of epsilon, and we get a true positive with a probability of 1 minus epsilon if the key does not actually exist. Okay. This epsilon is going to be called our false positive rate, or FPR. Alrighty, so high-level note, why should we even care about filters? Why am I teaching this? First of all, they are really, really widely used in systems. So if you're going to work in systems, you're going to encounter them in practice, and it's good to know about their different design decisions. But beyond just that, even if you're not going to be a systems person, filters actually provide you with a nice means to learn various hardware optimizations and algorithmic reasoning and general techniques, which will help you, I think, in computer science no matter where you go. Okay, so this is why you should pay attention. Today, we're covering static filters. So these are going to be kind of filters that do not support deletes or expandability, resizing, or contraction. If you want to modify the filter and the data that the filter represents, the filters that we're covering in this lecture, you have to rebuild them from scratch. Next week, we're going to have a whole lecture about dynamic filters, which provide you with delete support and resizability. This begs the question, if these dynamic filters are more richer in functionality, why do we even care about static filters? The reason is that if you want to get the fastest possible queries or the lowest possible FPR, false positive rate, you want to use a static filter. So dynamic filters cannot actually compete. Interestingly, though, we actually, even with static filters, we don't really know how to get the fastest queries and the lowest FPR at the same time. So we'll still need to use different static filters to achieve the best of these two possible metrics. Okay, and these two data structures that we're going to cover today, the first one will be the Bloom filter, but we're going to show how to really hardware optimize it. And the second, and by so doing, the Bloom filter will be very fast, whereas XOR filter is going to be slower, but be able to achieve a lower false positive rate. So we're going to see how. Okay, quick note. Today is going to be more mathematically intense than usual, but don't let that intimidate you. We're not generally going to have this much math in the course, but still, I think it's really nice to be able to follow the kind of math that I show here. I think this is good for anybody's kind of maturity and reasoning skills. Okay, so Bloom filters. Let's just recap what they actually are. So as most of you know, a Bloom filter is just, okay, and Bloom filters, historical note, come from this paper from 1970 by Burt and Howard Bloom. So they are over 50 years old at this point. Okay, so Bloom filter is just a bit vector with k-hash functions. All right, to insert a key, you're going to hash the given key that you want to insert using k-hash functions to k random bits in the bit vector, and you're going to set each one of these bits from 0 to 1, or keep the corresponding bit set to 1. Yes. So here we show the insertion of key x using just two hash functions, but the number of hash functions is generally k, not necessarily two. Okay, let's insert another key. You can see here y maps to a new bit, but also to one of the old bits, in which case we just leave the old bit set to 1 as well. Okay. So to query this thing, we're again going to hash a key to the k random bits that its hashes correspond to. And if all the bits are ones, we're going to return a positive to the user. Okay, so here's an example. We're checking for x. We actually inserted it. We get a true positive. However, if we check for a key that does not actually exist, in that case, we might encounter a 0. And if we encounter a 0, then we know for sure the key had not been inserted, right? If there is at least a 0, that 0 would have been a 1 if the key had actually been inserted. So we know it's a true negative, and we can return a negative to the user. Okay, however, if we could also check for a key that we haven't inserted, and that key by accident hashes to keys that are all ones. This is the case in which we get a false positive. Alrighty, note that this data structure does not support deletes. And why? Because multiple keys that we insert can share bits. And so if we set a bit from 1 back to 0, this could lead to false negatives when querying for some other key that still exists. Okay, and this is why we consider this a static filter. Okay. Here is the construction contract for a filter. We're still doing background. To construct a Bloom filter, and in fact, any kind of filter, or static filter at least, you want to know the number of entries that you wish to insert in advance. And you want to know the false positive rate that the filter, that you wish to guarantee to the user. You then allocate a filter with this number of bits, right? So this function depends on the false positive rate and on n, the number of entries. And then, just insert the entries as we spoke about using your k hash functions. We'll see what k should be. And if you follow this procedure, the filter will guarantee indeed a false positive rate of epsilon. Okay, so the key here is you need to know what the false positive rate is in advance and how many entries you want to insert in advance. Okay. All right. So to our agenda today. So far, this was totally background. What we're now going to do is we're going to analyze these Bloom filters, and we're going to do so from the ground up, and then we'll talk about two hardware optimizations, blocking and sectorization. Okay, so we'll do the analysis. I'm going to kind of speed through this as well, but this analysis, so in the course last semester, I also presented an analysis of Bloom filters, but over there, kind of handed you over some things, right? So we didn't analyze this from scratch. Here, we're going to run this analysis from scratch, just because there's something kind of gratifying about reasoning from the ground up and seeing where we get, right? And again, I think this is a nice thing for maturity. Okay, so we'll do this, but we won't spend too much time on it. And if you care about how to analyze these filters, right, you can go to the following paper, let's say, which has a really complete and nice analysis. Okay, so to analyze a false positive rate of a Bloom filter, we're going to analyze it with respect to the following three terms: the total number of bits in the filter m, the total number of keys that you insert n, and the number of hash functions k. Okay, now let's first of all ask, what is the event that causes a false positive to actually occur? Well, that event happens if all random bits that I hashed the key to had been set to ones by other keys, right? So that's the event that causes a positive. This is going to be a little bit complex to analyze off the bat. So what our strategy for reasoning about this is going to be to take this question and reduce it progressively to a series of smaller and more tractable questions. And then from these smaller questions, we'll come back and answer this more complex question. Okay, so first of all, we take this question. Let's reduce it to something a little bit simpler that is easier to reason about. What is the probability that some random bit has still not been set after n insertions? Right, so rather than looking at the k bits for a given key, I'm now looking at just one bit. Let's reduce that even further. What is the probability that some random bit had still not been set after one insertion? Okay, and in fact, we can reduce that more. What's the probability that some bit has actually not been set after we apply just one hash function for some other key? right? And this is easy to answer. This is just 1 over m, where m is the number of bits in the system. Okay. Let's negate that. What's the probability that a bit is still not set? 1 over this expression. Okay. Now, what's the probability that the random bit is still not being set after 1 insertion? Well, an insertion consists of k hashes. So this event should have not happened k times. Right? So we exponentiated by k. What should we do for this one? What should we do for this expression to answer this question of what's the probability of yes? Yes. Good. Okay. At this point, we're starting to get kind of a complex expression. So we can use some, probability tricks to simplify the expression. So this is a very well-known identity, right, in probability theory, that 1 minus m, 1 over m, all raised to the m is equal to 1 over e, right? And you'll see this as a kind of motif. This kind of simplification arises many places when you do probabilistic analysis. So we're going to arrange this equation in a manner that allows us to use this, then kind of plug that in, right? And simplify. And now we have a much simpler expression that captures this event. Okay, let's continue. Let's invert this question. What's the probability that the bit is set after n insertions? Well, it's 1 over this expression. And now what do we need to do to this expression to answer the final question? Take this and do what to it? So now we have the probability that a random bit is set after n insertions. You answer the last one. I'll let you answer this one too. Raise it to the k, correct. Okay, and this is our false positive rate. Okay. Everyone happy? Yes.
Set the probability of a bit being set after 1 insertion, being set after 1 insertion is 1 over n.
Yes.
Are we assuming that each insertion is 1 bit?
Each insertion, well, so that was an argument with respect to one hash function.
Right, so what is one hash function setting 1 bit?
Yes.
Okay, because like the diagram before showed that was setting 2 bits. So
okay. So I'm sorry if there was ambiguity in the visualizations, but generally speaking, each insertion of a filter, of a Bloom filter, right, it uses k hash functions, and each one of these hash functions maps to 1 single bit.
oh, okay, that makes more sense.
Good. Okay. So let's go back to where we were. Okay. Okay, good. Let's continue. We're still kind of speeding through this, so I just want to cover it, but I don't want to spend too much time on it. How many hash functions should we use? Right, so it's pretty clear that if we use too few hash functions, right, the false positive rate is not going to be that great. If we use 1 hash function, the false positive will happen as soon as we hit a single bit that's at 1. Right, as we use more hash functions, initially what's going to happen is a false positive rate will become less probable. But if we use too many hash functions, each insertion will set a lot of bits, and that in turn will start to increase the probability that we get a false positive, right? So there is a curve here, and the curve looks something like this, right? So if you analyze the false positive rate with respect to the number of hash functions, you'll see a curve like this, and you can actually optimize this. So optimize the false positive rate with respect to the number of hash functions to optimize the false positive rate. So this you can do mathematically. Take the expression that we derived before, differentiate it with respect to k, and you get this expression for the optimal number of hash functions, log of n times number of bits per entry that you're using. So nice. Okay. Good. Now, okay. So now we have the optimal number of hash functions. We would like to have a false positive expression that's independent of the number of hash functions, right? Because we know the number of hash functions from this equation. So let's take the optimal number of hash functions, plug that into the expression for the false positive rate that we derived before, right, and simplify, and we end up with this much simpler expression, which gives you the false positive rate under the assumption that you're using the optimal number of hash functions. Okay, and this is the expression that I gave you last year. Right, last year I just handed you this expression and told you, believe me. Now we have derived this from scratch, right, which is kind of nice. Okay. Okay, and now you can take this equation, vary the number of bits per entry on the x-axis, right, and see what kind of false positive rate you get for different numbers of bits per entry without even caring about the number of hash functions you're using. It is implicit that the number of hash functions is optimal if you're using this equation. Okay, let's now turn to analyzing the performance of the Bloom filter. And here I will substantiate another assumption that I made when we did this last semester. Take the optimal number of hash functions. Take also the expression for the probability that some bit in the filter has still not been set, right? This is one of the kind of building block expressions that we had when we analyzed, when we tried to get the complete analysis for the false positive rate. There's a question?
So for each point in the graph, actually the optimal number of hash functions is constantly changing because m is changing.
Yes.
And then number of hash functions is constant m.
Correct. That's exactly right. Okay, take the optimal number of hash functions, plug that into this expression that we have seen a little bit before in the FPR analysis. This is the expression that some bit is not set after right after we finish construction. And we get 0.5. Take that, simplify, you get 0.5. What does that actually mean? That means that 50% of the bits after you've constructed the filter are set to zeros, and the other 50% are set to ones in expectation. Right? So again, this is something that I just told you last year to accept, but here you see how to actually derive this from scratch. Okay, why is this important that 50% of the bits are zeros? It's important because this is going to allow us to reason about performance. Okay, let's now reason about the costs of the different operations. For each one of these operations, we're counting the number of hash functions we have to compute per operation. Note that each hash function also corresponds to a memory access, right? And this is usually how we measure performance in terms of the number of cache misses that an algorithm has to perform. For an insertion, we have to go to k hash functions. This is the optimal number of hash functions. This is the number of bits that we have to access for an insertion. Okay, so far I haven't said anything too interesting or controversial. For a positive query, each one of the bits that we're going to check is going to return a 1. We have to check all of them. So again, it's just the number of the optimal number of hash functions. But now for a negative query, here we're now going to use the fact that we know that 50% of the bits are set to zeros. The reason is that we have an opportunity to terminate a negative query early. We can terminate the query as soon as we encounter the first 0. As soon as we encounter the first 0, we know the key cannot possibly exist. But we know that 50% of the bits are set to zeros, which means that for each bit that you access, there is a 50% probability that it's a 1 in which case you have to continue, or a 0 in which case you can terminate. So you can reason about the expectations, like how many bits you have to look at on average before you encounter a 0, and you can simplify that out to 2. And now we have a complete analysis of everything you've seen from last semester from scratch. Yes?
I remember, right, we only said, I think we didn't have a divided by n for the optimal number of hash functions. We only had like n minus 3.
You're right. I changed terminology a little bit. So last year, okay, correct. Good. Thank you for that. In the slides last year, I think I actually assumed that m is denoting the number of bits per entry. Here I'm saying m is the total number of bits in the filter. So m divided by n is the number of bits per entry. Thank you for that clarification. Okay, other questions? Okay. Okay, so now things are going to get a little bit more interesting, and we're going to start introducing some new things and concepts. So are these performance characteristics okay for modern hardware? Okay. Well, what are your takes? Okay, well, let's first of all understand a few things. So the filter is supposed to reside in memory, right? And this is kind of an illustration of what the modern memory hierarchy looks like. So you have memory, you typically have 3 layers of caches with different sizes, and finally you have some CPU registers. Okay, so data moves from RAM across the different levels of across the different CPU caches at the granularity of a cache line, right? And a cache line, it varies on different machines, but for this lecture, let's assume that it's something like 64 bytes or 512 bits. Okay. However, to actually process a piece of information, that happens at the granularity of a word, 8 bytes. Right. So when something is in the L1 cache, you want to actually read individual words from that cache line, bring them to the register, and process them. Okay. So in terms of latencies, right, bringing a word from the L1 cache to the registers takes you something like 3 to 4 cycles. Bringing something from L2 to the registers, 10 to 12 cycles. From L3, 30 to 70 cycles. And from DRAM, 100 to 150 cycles. Okay? Now, this is all based on numbers from 2016. Probably things change a little bit, but then again, probably not by too much. Okay. So returning to this, what's the issue? Assume that the whole Bloom filter is in memory. Yep. Sorry? Ah. Okay, sorry. This should be m divided by n. Thank you. Sorry. I'll fix that. Okay, so what bad thing can happen for each one of these hash functions that we compute? Yep.
This is the worst case. If you have a lot of bits in your filter, your data would be large enough. It's possible for every one of the k hash functions that you have to access some bit or whatever, right? You have to like load it all the way from the like so inside every single.
Exactly. Exactly right. Right? Yeah. So each one of these hash functions can end up leading to a cache miss. Right? And what did we say about the latency of a cache miss? Something like, let's simplify and just say 100 nanoseconds. Not that cheap. Okay, so ideally we want to do better than this. Okay, so this is what we're going to try and do throughout this lecture, but we're going to see that there is actually some sort of contention between getting these costs down to improve performance and actually maintaining a good false positive rate. So the challenge will be how to maintain both at the same time. So here's an observation. The basic Bloom filter is actually the slowest kind of filter that there is. If you compare it to any other filter that is actually in use today, it's just the bare bone filter, Bloom filter that we've seen so far, it's the slowest because of these random cache misses that it has to perform. But interestingly, with the hardware optimizations that we're going to see, it actually becomes the fastest. Right? And as we'll see, there are aspects of the Bloom filter that really lend themselves to hardware optimization, much more so than other filters that we'll see. Okay. So as we said, the issue is that each hash function can lead to a cache miss. What can we do to avoid this, to make things better? I think you know the answer because you took the course. Yes. Does somebody else want to give some intuitions? Did everybody catch that? Okay. So so basically that's right. So, okay. So this idea comes from the following paper. This is a block Bloom filter paper from 2010. And today, most Bloom filters I know actually use this idea. So instead of hashing each bit to all these different random locations in a bitmap, what we're instead going to do is, first of all, map each entry to a particular cache line, or let's not say a cache line yet. Let's just say that we're dividing the filter into blocks right? And I'm first of all going to map an entry to a block. Once the entry has been mapped to that block, then I'm actually going to insert the entry into that block as though that block is a totally independent Bloom filter. Okay, that's the core smartness. Okay, and what does that allow me to achieve? Why should I do this? Why is this good? One cache miss, right? So for every insertion and for any query, at most one cache miss because all the relevant bits that I need to access are within the same block. I guess I'm assuming here that the block is the size of the cache line. As we'll see, it's actually a very good thing to set the size of a block to the size of a cache line. But I'll argue that more in a little bit. Is there a question? In some sense, yes. Although, if you want, you can also kind of derive like a big hash up front and then use different bits from that hash to do all you need to do. Okay. Okay, so this gives me one cache miss for query and insertion. What bad thing happens if I do this? And right, somebody that doesn't already know, some of you know because you've seen this before. Yes. Yes, that's exactly the bad thing that can happen. What's your intuition about why?
The analysis part and computer randomly assign all the bits. We have this subset that now we're restricting that bits we can send to. I'm worried that I guess the other entries would also be in that small subset.
Yes. Yes. So that's good. That's exactly right. And now we're going to substantiate that. So rather than just, kind of having the intuition that this could mess with our false positive rate, right? Then, intuitively, there's less randomness in this design. We're kind of enforcing constraints about where each entry should go. There's less randomness, so it's going to mess our false positive rate up. But instead of just accepting that as an intuition, let's try to actually reason about that formally. Okay, so the core issue that these blocked Bloom filters lead to is that you now end up with on average the same number of entries in each block, but you actually have a distribution, right? It's not going to be the case that the number of entries mapping to each block is going to be identical. In some blocks, it's going to be more. In some blocks, it's going to be less. So how does that impact the false positive rate? Well, what we're going to do now is introduce a reasoning technique that's generally applicable for hash tables, right, to allow us to really tackle this question. Okay, so before I show you the actual technique, I'll show you why we use that technique and why that technique makes sense. Thing to observe is that if you're trying to analyze the number of entries that map to a block, right, this is going to follow a binomial distribution, right? So in this binomial distribution, n is the number of entries, p is going to be the probability that you fall into a given block. Let's say 1 over n if n is the number of blocks. This is not totally precise, but I'm just trying to build intuitions. And I is going to be the probability of I entries falling into that block. Right? So why is it binomially distributed? Well, this choose term is going to give you the way of choosing, this should be I elements out of the different n entries that exist. And then, this is the probability that, again, I of them will fall into our block. And this is the probability that all the other ones that you've chosen will fall into other blocks. Okay, so this is kind of why it's binomially distributed. But this formula is also a little bit cumbersome to work with. So instead, we're going to observe that for a large n, the binomial distribution can be approximated by the Poisson distribution, which is much more convenient to work with. Okay? So this is stuff that you probably know from probability theory, maybe for some of you years ago, but anyway, I'm just trying to justify where the technique comes from. Okay, so now we're going to reason about the number of entries I that fall into a given block, and I'm going to say that's going to be distributed based on the Poisson distribution, right? Where this lambda, the average of the distribution, is going to represent the average number of entries per block. Okay? What is lambda going to be in our use case? Well, let this be the number of bits per cache line. So this can be 256. Let m divided by n be the number of bits per entry. Right, so on average, this is a number of, this expression gives me the number of entries on average per cache line. Okay. All right, so if you plot this distribution, you're going to see something like this. So this is drawn for, lambda equals 16. And what does this distribution tell you? That, on average, 16 entries map to each block in this case, but you're going to have, these blocks in this side of the distribution that underflow, they were assigned too few entries, right? And these entries on the other side of the distribution that overflow, they were assigned too many entries. Okay. How do we use this to reason about the FPR? Well, okay, so now we have the first building block. We have this distribution. We're also going to take the false positive rate expression from before, right? This is the non-optimized one for K. And okay, so with this expression, we have, right, this expression gives me the false positive rate, assuming a filter with B bits. I have B bits in my cache line. I have I entries in a given block. And let's say I'm using K hash functions. Now I can just take these expressions, multiply them by each other to get the weighted average. All right, so this is going to give me the weighted average of the false positive rates across all the different blocks in the filter, right, based on, the distribution. But so this is going to account for the fact that some blocks underflow and other blocks overflow. Okay, this expression is actually, it's hard to compute in closed form, but you can actually plot that in Excel. All right, and if you plot that on Excel, you'll get something that looks like this. So what does this curve mean? So this curve is varying the number of bits per entry. It's increasing it on the x-axis. It's measuring the weighted false positive rates across all the different blocks. And it's saying, if my block is very, very small, okay, that's going to damage the false positive rate by quite a lot, especially as I'm adding more bits per entry. As I'm using larger and larger blocks, I'm allowing more randomness in some sense, more flexibility. And so I'm able to achieve a better false positive rate across the board. So what does this tell us? This tells us I don't want to set the block to be too small. I don't want the block to be, say, 32 bits, right? An extreme situation would have been just to say, let the block be not a cache line, but just a word. Yeah, but this tells us that this is a bad idea, because if we set the block to be too small, it's really going to mess with our false positive rates. What this graph is showing you is that if you set the block to be approximately a cache line, we don't actually lose that much compared to a regular filter. And this is nice. Okay? So this gives us the motivation for sizing blocks as cache lines and not anything smaller. Okay. Excellent. Everybody with me? Questions? Good. Let's continue. Okay. Okay, are we done? So far, I've talked about blocking. As I told you at the beginning, there is also another technique that we want to talk called sectorization. Okay, so there's still okay, so I'm giving you a hint that there's still an issue here. Can anybody kind of foresee what that issue is? So we've mapped all the different hash functions to a single cache line. But each one of these hash functions is actually still going to access a random bit in the cache line. Is random access within a cache line okay? Or is it slower? Discuss. Any intuitions? Yes?
But that function, the first one, hash function, then the last one, you have to load the other cache line.
Correct. That's right. That's right. So basically, is that another intuition there? Exactly.
Register. So that's like another control. Yes.
Exactly. Exactly. Any other intuitions? Yes?
So like, still encourage random access within it, so you cannot leverage something like the prefetcher or something.
Also true. Yes. Yes. Okay, excellent. So I think you got the intuitions. the basic problem is that even though we've mapped all the hash functions into the same block or cache line, we still have to perform random access within that cache line. Okay, and why is that bad? That's bad because we don't need to just stop considering things when, they're in the L1 cache. Exactly as, was pointed out by one of you, there is still a latency of moving a word from the L1 cache to the register, right? That's going to be 3 to 4 cycles. So we don't want to thrash the words inside a cache line. Okay, so the issue here is that each random access to, given by a different hash function, it's going to move a different word from the L1 cache to the register. I'm just saying the same thing over and over. Let's just see this in action. Let's just see how this problem actually manifests. And for this, let's suppose for a second, let's suppose that our block just consists of 2 words, okay? And let's suppose that we're using 4 hash functions. Here's the issue. Let's suppose my first hash function happens to map to the first word. My second hash function corresponds to the second one. The third hash function goes back to the first register. The fourth hash function again goes to the second one. Okay, I've just given you a kind of like the worst case that can happen. So what can we do to mitigate? At this point, now that you've seen this kind of bad situation, how should we fix this?
What if you like, we wanted this blocks, but within blocks again.
Excellent. Okay, so how? Be more precise.
So inside a block, we're gonna again divide it, and if the block is the size of your cache line, then we'll make each section inside the block the size of the.
Yep, that's exactly what we're gonna do. So okay, so this is called. There are different words to this. There are different terms for this. So I think the person credited with coming up with this design is a guy called Jim Apple. And you can read about his write-up about this idea in a paper called Split Block Bloom Filter on the archive from 23. But I think this design has actually been used by the Impala database system since 2016. And one of the papers that you were assigned for the reading for this week looks at this idea and extends it more and really kind of studies it in detail. Okay, so the basic idea, as you pointed out, is to take the block and partition the block further into, let's call these sectors. And these sectors are equally sized. And let's say we have S of them. Okay, so let's zoom in. So here's the block. Here are a bunch of sectors inside that block. All right, here we have 4 sectors. Okay, what I'm now going to do is I'm going to take my hashes and I'm going to divide the hashes that I apply equally across all the different sectors, right? So if I have K hashes and S sectors, I'll apply K divided by S hashes to each one of the sectors. And so this is what it's going to look like. Suppose that I have 4 sectors and I'm using K equals to 8 hash functions. I'll begin by hashing 2 bits over here. The way in which this will actually look is I'll probably, first apply these hash functions on some other register, and then I'll just OR it with the contents of the actual sector that I want to change. All right, and I'm going to do that for all the different sectors sequentially. And why is this nice? This is nice because I only read 4 sectors at this point, rather than thrashing, which could have led to, having to read 8 words, right, rather than 4. Okay. How should a query work? A query is also going to look at K divided by S hashes per each sector. So the query is going to be a little bit different. Let's suppose that the query is going to, again, apply its hashes to a separate word. Then it's going to end it with the particular sector, right? And then compare it to itself. And if it's the same, it means that the bits actually exist, right? And then I can just, if they're not, I can just return a false. The key doesn't exist if there's, if they're not equal. But otherwise, I can just continue traversing all the registers. And if I don't find any 0, I can return a true to the user. Okay, so just so that we can appreciate a little bit the performance impact of this thing, let's look at the following figure. And this figure is from the paper. Okay, so here Okay, so this is just with a blocked. Let's pay attention to the blue one first. With a blocked filter, here we're starting with a very, very tiny block. This is a very tiny block with only one that only spans one word. Performance is great for here, but the false positive rate is not going to be so great because it's a very small block. Now, what happens as we increase the block? Well, as we increase the block to just 2 words, immediately thrashing begins to happen. And our lookup throughput really, really decreases significantly. Okay? And it kind of just stays bad, as you increase it, right? Because thrashing happens here. With the sectorized filter, right? If I only have one word, these two designs are actually equivalent to each other. That's why they meet here. But here, as I'm adding more and more words, because I'm traversing these different words sequentially within a block, there is a much more graceful degradation in terms of throughput. Okay, so these things actually matter. All right. Questions? Complaints? Yes.
So we sectorize it even further. How will that affect our FPR? Because if blocking it affected, it will not affect it.
So how does sectorization affect the FPR? Yes, let's get into that. That's a great point, and you're exactly leading to the next part. But before I get to that question, are there any further ways in which we could optimize the sectorized filters? Perhaps some of you have seen AVX or SIMD operations before. So if you're kind of smart and very hardware conscious, you could actually perform the operations on the different sectors in parallel. If you're using SIMD operations, then things become kind of platform dependent, but you could actually do this in parallel. And right, the fact that you know exactly how many hash functions to compute for each sector is precisely what allows you to use SIMD here in this context. Okay, and now back to your point over here. Are there any problems with these sectorized Bloom filters? We're having a break very soon. Do not worry. Are there any problems? Yes. The problem is that, okay, I already flashed it to you, so I'm not going to ask you. The number of hashes must be a multiple of the number of sectors, right? So this is a constraint. And why is this constraint bad? Yes? Yes, exactly. This is going to force us to use a different number of hash functions that might be different than the optimal, and this might mess up our false positive rate. Okay? So, as always, how can we solve this? Yes. Okay, so I like how you're thinking, right? So, okay, so there might be different solutions to explore here. Let me show you how the paper is addressing this. They also show that, the solution that they propose is, strikes a pretty good balance between performance and FPR. That's not to say that any of the things that you said here are, invalid. Maybe they could work too. Maybe they could even work equally well. But let's just show how the paper actually solves it. The paper divides this further. It actually groups the sectors. So now it imposes these groups. The number of groups is larger than the number of blocks, but smaller than the number of sectors. So here I have 2 groups. These 2 sectors belong to this one. These 2 sectors belong to this one. What I'm now going to do is map each key to just one group. And within that group, I'm going to map it to one sector. Okay, and then within the sector that I map it to, I'm going to apply however many hash functions I want to. And as you can see in this example, this allows me to use 6 hashes, right, which is not a multiple of 4, the number of sectors. All right, so by further restricting my flexibility in a way, by using these groups, I can actually now use, I have more flexibility in choosing the number of hash functions. Okay, the paper will actually show you a performance figure that shows you that this design achieves a near optimal false positive rate and a near optimal performance. I'm not going to show you the figure here, but you could look at the paper to view it. Correct. So the number of groups is going to be a power of 2. The number of sectors is going to be a power of 2. The thing that's not going to be a power of 2 is the number of hash functions per group. Yes.
What is the optimum set?
The optimal number of hash functions?
What if it's set?
Too bad. Too bad. So this gives you some flexibility, but not all the flexibility that you want, right? So so yeah, maybe you can't be perfect. Maybe this is why they can't totally reach the optimal false positive rate. Good point. Okay, any other comments? Okay, so let's take a 5-minute break. Let's alrighty. So what we've seen so far is that the Bloom filter gives us a false positive rate, kind of like this expression. And, in fact, if we're using all the hardware optimizations that we mentioned, it's going to be a little worse than this expression. But let's say that if we're being smart, like, with the, kind of grouped sectorized filter, we can actually kind of be close to this while being hardware optimized at the same time. Okay, but here's a question, and it's kind of a theoretical question. How far away is this from the best you could possibly do in terms of the false positive rate? Right, so I'm asking a very theoretical question. I'm asking us to actually derive a lower bound for what the false positive rate for a filter should be. And then I want to check how close the Bloom filter is to that lower bound. Okay, so this is what we're going to start doing. Is that a question? No. Okay. Okay. So here's how you start reasoning about this. Our analysis here is going to assume nothing about the implementation of the filter. So for all we care, we don't have a Bloom filter. We just have a Bloom filter. Sorry, we don't have a Bloom filter. We just have an abstract filter, and we just know its specification. And we're going to reason about that filter in terms of its specification, but not with respect to its internal implementation. And what do we need to know about its specification? Well, we need to know the following things. What FPR are we trying to guarantee? How many entries are we inserting? And maybe also what the universe size is. Okay. Okay, so before, as a warm-up exercise, so a filter can be seen as an approximate set. As a warm-up exercise, and actually this would be a nice building block for our derivation of the lower bound for filters, let's first of all reason about what is the lower bound for an exact set. And what do I mean by this? Suppose you're trying to represent an exact set. What is the least number of bits that you need to be able to do so? Okay, so in particular, we want to answer the following question. Out of universe of U entries, we want to store N entries, right? What's the least number of bits that I need to be able to do this? Does anybody have an idea? Yes, back there. Yes, you. Log 2 of U. That's actually going to be a little bit wasteful, because so you're talking about representation per entry, right? So if you're doing log U, what that means is you're doing one binary representation for each one of the entries that you're actually representing. Turns out you can do better. That doesn't give you a lower bound. That gives you like maybe what you would have if you use a binary representation to represent each entry. Any other ideas? Yes? N? Okay, the expression is going to be proportional to N because we need to store some bits of information for each data entry N. But what your expression doesn't yet capture is how many bits per entry do we need to represent. It's not exactly N, it's going to be a bit higher than N. Okay. Here's an insight. What are all the different ways in which we can choose? Let's reason about all the different ways in which we can choose N entries out of a universe of U. Okay. There's only so many, right? And this is an expression we can compute precisely. And then let's say for each unique combination, we're going to assign a unique binary encoding. to encode that combination. Right? That's the least number of bits that I need. Does everybody kind of follow that? Yes? That what has what order? If you're assuming something about order, this is going to be something like n factorial. Yeah. But because it's a combination, because it's a set, and there's no notion of order here, I only care about combinations rather than a permutation. Okay. Now I'm gonna snap my finger and tell you that this expression for a large U actually simplifies to the following. Right? They're quite similar when U is large. N times, right, this. Right, so you can kind of see, like, now you can start getting some intuitions, right? This is showing that for every entry in my set, I need to represent not log of U. Log of U would be like a binary representation to encode each element uniquely, but I actually need fewer bits per entry than that. Right? And the intuition, as you can see here, the number of bits that I need is actually decreasing with n. Right? The intuition is that as my key space is becoming more and more and more crowded, there are kind of less ways of choosing n entries. In some sense, it's like the distances between the entries decrease, so there's less information to encode. Just giving you an intuition. Okay. Okay, so this is our lower bound for an exact set. Let's now try to reason about an approximate set. Okay, so to do that, we're going to apply the following inequality. And this is a little bit weird, but what this is saying to you is, let's suppose that we have a filter. What is the least amount of information? And a filter is an approximate set. So this is saying, what is the least amount of information that I have to add to that filter to transform it from an approximate set to an exact set? Right? This is kind of the intuition for why I'm presenting this. And I'm saying that the filter plus this disambiguation table, this disambiguation table is actually going to resolve the true positives from the false positives. By so doing, it's going to turn the filter from an approximate set to an exact set. Okay, so this is my high-level strategy for proving this. All right, this is my legend, my list of terms. Okay, so this is just what I said. The disambiguation table is what information must we add to the filter to turn it from an approximate set to an exact set. The exact set, I'm actually just going to apply what we derived before, right? The lower bound for an exact set. And then here kind of comes the fun part. Conceptually, I'm going to query my filter U times, one for every entry in the universe. I can do this because I don't care about time in this analysis. Okay, I only care about space. But once I query the key for every possible key, the filter for every possible key in the universe, what does that tell me? That tells me precisely what are all the keys that return a negative versus what are all the keys that return a positive. Right? I don't know which positives are true or false. I just know out of the entire universe which keys are negative and which are positive. And how many keys are positive, I can reason about that. I know that n entries lead to true positives and epsilon times u lead to false positives. All right, so this is the number of keys in the set that lead to positives. And then, okay, I'm actually going to assume that u is very large, so u is going to dominate that n term. I'm doing that for simplicity. And then, does anybody have a sense of what I need to do next in this proof? Yes? Say that more loudly. Yes, exactly. And what would be the size of the set? Do you have a sense? Epsilon times u, close, but basically what we're doing now is we're creating an exact set that tells us of the positives. Now in some sense, I'm restricting the universe to just the positives. Of the positives, give me an exact set that tells me which ones are the true positives. Right? So tell me which ones are true out of this universe size. right? What is the size of that? We're just going to apply exactly the same reasoning as we had for an exact set before. The number of different combinations for that is the number of positives, epsilon times u, choose n. What is the size of this? The size of this is, again, take the log of that, simplify to the expression that we saw before, plug that in, okay? Take that and subtract that from the other side and simplify. Okay, and this gives us the lower bound for a filter, right? So this is kind of satisfying, all right? If we show that we cannot do any better than this, and we were able to show this without saying anything about the filter itself, anything about the implementation, just about the specification. Okay, all right, and if you want to rearrange that in terms of epsilon, you can do that. And that in turn tells you that the lower bound, right, for the false positive rate is this if you have this number of bits per entry. Okay, so now we're back. Now we're back to the land of real data structures. And now we can see that there is this discrepancy between the false positive rate that we managed to achieve for a filter versus like the idealized lower bound. So there's, what does that show you? When you have an upper bound that doesn't meet the lower bound, it either means that your lower bound isn't tight, or it means that there's maybe potentially a better algorithm that can approach lower bound. And as we're now going to see, there is indeed another kind of, it's actually a family of filters that allow you to move away from where the Bloom filter is on that spectrum and move closer to the lower bound. Right, that's going to be the XOR filter, which we're going to see now. And it's going to allow you to improve that exponent to 0.81 from 0.69. But there are actually all sorts of improvements to the XOR filter that actually really allow it to approach the lower bound. We're not going to talk about them in detail, but at least we'll show this step. Okay. Everybody with me? Any questions? Yes.
Clarify what you meant by the universe. It's like an unordered set of like key spaces.
So to reason about the universe, I guess I have to, the easiest thing is to just assume that my keys are fixed length. If they're fixed length, then, let's say that I'm representing integers, each one of them 4 bytes. There are only so many integers that you can represent with respect to 4 bytes. So that's the universe size. Okay. Yes.
I guess like intuition behind XOR filter, is it similar to, when we talk about parity bits and filter trees, in risks? So it's like,
We talked about the XOR operator. We talked about
what's the parity bits in storing redundant information? I forgot what the name was. RAID, yes, sorry, yes.
yes. Yeah, it's going to follow a lot of the same. It's going to use the same building block as RAID. It's going to use XOR operator. Okay. Other questions about what we just did with the lower bound and kind of the story so far? Okay. So let's get into XOR filters. So this comes from a paper from 2020, although kind of similar ideas have been around for a longer time. There's a paper called Bloomier filter from maybe 20 something years ago, which also has very similar concepts to this, but we're going to focus on this paper. And before I talk to you about like what the actual paper does is, let's do a quick recap of the XOR operator, because XOR operator is going to be a crucial building block in this design. So here's XOR operator for those of you, just to remind you, the XOR operator takes 2 different strings of bits, stores them. What does that mean? It means that if both, kind of bits on top of each other are 1s, you get a 0. If one of them is a 1, but the other one is a 0, you get a 1. And if both of them are 0s, you get a 0. Okay? Why is XOR helpful? It's helpful because it allows you to, okay, so the product of XORing is called a parity. And this is helpful because supposing that you lost either one of the inputs, but you still have the parity actually allows you to recover the other input if you XOR it with one of the original inputs, right? So if I take input 1 and XOR it with the parity, I will actually have recovered input number 2. Okay, so this is something that you've seen in the course last semester in CSC 443. And this works for any input with a parity. So I can also apply this with input 2 and the parity to get input to recover input 1. Okay, now this operation is associative and commutative, meaning that given any number of inputs, you can XOR them and derive a parity. And then if you lose any one of those inputs, you can still XOR all the other inputs with a parity to obtain the one input that you lost. Okay, excellent. We're going to use this as a building block, but does anybody have questions about this? Okay, so the XOR filter is going to use XOring, but at a more basic level, what this filter is doing is it's storing a fingerprint for each key. And a fingerprint is just a hash digest that you derive by hashing the key. Okay, so for instance, suppose here my key is X. I'm going to hash X into a fingerprint, and in this case, the fingerprint has 4 bits. F is 4. Okay, so this is kind of what the query workflow looks like. A query for a given key is going to generate the fingerprint for that key, and then ask the filter, does that fingerprint exist in the set of fingerprints that you're representing? And if it does, we're going to return a true positive, but we could also get a false positive if there is by accident some other matching fingerprint that had been inserted by other keys. Right? In this sense, this is kind of similar to cuckoo filters, which you've also seen last semester. Okay. How does XOR filter actually store its fingerprints? Here is where things kind of get interesting. So the XOR filter is going to take each key that you want to insert, and it's going to map that key to 3 random slots in an array. And each one of these slots just has space for 1 fingerprint. Okay, F bits. Okay, so I'm mapping each entry to 3 different slots. And then what I will do is I will assign each slot to uniquely own one of the keys. I'm going to do that during my construction algorithm. Ultimately, and then, okay, so I will assign 1 slot to own each key. And what I will then make sure that I will construct the filter such that if I XOR the 3 different locations that the entry maps to, I'm going to recover my original fingerprints. Okay, that's going to be my strategy. So I will start doing this. I will start running this thing by, first of all, mapping it. Okay. Does that sort of make sense? Does that intuition make sense? We're gonna really break this down and look at the construction algorithm, but does the high level story make sense? Okay, I think it's going to become a little bit more clear as we see the construction. Okay. Okay. So the first step that we're going to do is we know we're taking each key and we're mapping it to 3 different slots. And as we said, our first kind of step in the construction is to get each slot to kind of uniquely own each key out of the 3 different locations that it maps to. What does that actually look like? To do that, we're going to use an algorithm called peeling. That's the outcome. So having 1 slot uniquely owning each entry is the outcome of the peeling algorithm. Let's kind of look at, so here's a very concrete example. Here are 4 keys, right? And each one of these 4 keys maps to the following 3 slots. Right? Okay, so this key, for instance, maps to 0, 1, and 3. Okay, so now I'm going to apply the following algorithm. While not all keys have been assigned a unique slot to own them, I am going to find some entry that only maps to a single slot. It actually turns out that there is a high probability that this is going to happen, that there's going to be some slot that only 1 entry maps to. In this case, it's slot 7. Right? You see no other slot, no other entry here maps to this slot. So this is why this is a good candidate. And then I'm going to assign 7 to be the unique owner of this entry. And I'm going to continue doing this, right? And as I actually assign entries into slots, I have more flexibility with respect to the other entries, right? Conflicts get eliminated. So now I see that, zero, the only entry mapping to 0 is this entry over here. So I get to assign this one uniquely to 0. And now I see that of the entries that are left, only this entry maps to 1. So I'm allowed to assign the square to 1, and then I only have one entry left, and I can just assign that to whichever. Okay? Now each slot owns one entry. Any questions about this? Yes.
So I think the insertion, it was different, maybe different than this. I think it's also an impossible. Like this not mapping, it's not mapping.
Correct. This does not succeed with 100% probability. We're actually going to reason a bit about this heuristically later on after we talk about the construction. But if this doesn't succeed, what should we do? Yes. So this is a static filter, right? So for a static filter, we just need to construct it once. That means that, for this kind of filter, we can spend some more time on construction time. Once it's constructed, we just want it to be fast. But basically, if the first time that you try with a given set of hash functions doesn't work, try some other hash functions, try from scratch. And with high probability, you will only need 2 times. Okay. Okay, so now that we've created a unique assignment between the different slots to the different entries, now we're going to actually start generating the bitwise content of the filter. What we'll start by doing is to take the slots to which I haven't inserted anything or mapped anything, and I'll just set those to be zeros. My first step. And now what I'm going to do is, again, in each step, I will take some entry to that. So I take this entry here, right? I have to choose an entry for which all of its neighbors, and let's say the neighbors are the other 2 possible locations that entry could have mapped to. So I pick the next entry for which the other 2 possible locations are substantiated by bits, right? And this also happens, there's a reasonable probability that this happens, right? So, for this triangle, even though I assigned it uniquely over here, right? The 2 other slots that it could have mapped to are empty. They're both totally zeroed out. So this is a good candidate to begin with. So I'm going to pick that element. And what I will do is I will XOR it with all of these neighbors. Right? So I'm going to take the fingerprint for this element and XOR it with the current contents of its neighbors to derive a new set of bits. And these sets of bits are going to be the ones that I store here in this slot. What does that guarantee to me? That guarantees that if I ever search for that key again, all I need to do is to go to these 3 slots, XOR them, and I derive the original fingerprint. Right? So let's continue with this. Let's take the square. So this is the fingerprint from the square. I get this fingerprint by just hashing the square. Then I also observe that the 2 other neighbors of the square, 3 and 4, right? These slots are now populated. So again, I'm going to take these slots, I'm going to XOR them with a fingerprint here, derive this set of bits, and this is going to be the set of bits that I store here. And again, that means that if I want to search for the square, I go to the 3 random locations, XOR them to derive the original fingerprint. I continue doing this. I'm now doing it for the star, XORing it, deriving the set of bits, storing it back here. And then for the last entry, right, I'll read those 2, XOR them, and store that at 7. Yes?
I think it's like 1, 4, 5.
Thank you. Thank you. Okay, that's to be fixed. Okay. And now we're done with the construction. So this is the construction. Yes.
Like we kind of just brushed off as high probability events for like things that might go wrong. So just intuitively, I'm guessing you need a lot more slots, the number of keys at least for the high probability.
Yes, that's exactly correct. This is exactly where the analysis of the false positive rate actually comes from. So you're right, we completely brushed it off. This is actually going, so this we're going to analyze kind of experimentally. But if you're curious, you could look at the papers for the precise analysis. But I will just kind of tell you what the results are for this. At any rate, just to remind you, a query for a given key now generates the fingerprint for that key and is then going to go to the 3 random hash locations, XOR them, derive what should be the fingerprint if the key exists. In this case, this is not the original fingerprint. So this is a query that's going to return a negative. Okay. Okay, so now let's get to the issue that construction can fail if there's no available entry that we can peel. Okay, so here is actually an example of this. All right, so this is an example. Okay, so I think this is an example where you have a circular dependency, where you cannot actually assign any entry uniquely to one slot. Okay, so this is really the issue. And as we said, if we fail, we must restart this algorithm from scratch. And exactly as you pointed out, Barth, to be able to succeed with a higher probability, we need to have some free space in the filter. So we need to make sure that some slots are empty. Right? This is going to determine the space utilization for this data structure. Okay, so then we might ask, what's the interplay between and in fact, the number of hash functions is also something. I've said 3, but why use 3? Okay, so I'm going to show you the following empirical results. So I guess I'm hand-waving here a little bit, but what I'm saying here is, let's suppose that I'm varying the number of hash functions that I'm actually using for this construction on the x-axis. And here on the y-axis, I am basically showing you the amount of space, the space utilization that I need to be able to succeed construction with high probability. Okay, so as you can see, if I'm using too few hash functions, in some sense, I don't have enough flexibility to map entries uniquely to slots. But if I'm using too many hash functions, right, then I have a situation where too many entries hatch to each slot. And that also makes it harder for the peeling algorithm to find a unique assignment. So here too, there is, kind of an optimization thing. This is very much kind of like optimizing the number of hash functions for a Bloom filter. And empirically, the optimal number of hash functions is 3. And given 3 hash functions, right, the empirical result is we need something like only 81% of the filter to be populated for us to be able to succeed with high probability. Right, so this is empirical. I think the analysis for this does get hairy, but if you're interested, this could be fun to explore. Okay. So this is how the XOR filter achieves this space guarantee. Is everybody okay with this? Okay. Suppose we want to do better than the XOR filter. So the XOR filter relies on having some free space, right? Some free slots for me to be able to complete the peeling algorithm with high probability. Does anybody have an intuition of, maybe using a different approach rather than peeling to create that unique assignment so that I can use less space? Okay. So this becomes hairy. There are various algorithms that have been proposed to do better than XOR filter. So for instance, ribbon filter is a variant of the XOR filter. And what it's actually doing is it's solving a system of linear equations to be able to assign each entry uniquely to a slot. So in some sense, this filter is trading even slower construction time to be able to use the space more efficiently. Yes?
They kind of involve minimizing the number of intersections or somewhere between these.
I think something like this. Yes.
I was thinking because, like you said, like you start from a slot which has nothing assigned to it, right? Like there's a high probability you won't find it, but what would you do if there was the case? I was like, I would just intuitively just minimize it and then keep going with because if there's more like hits on a single slot, or would want to prioritize it less than something which is like more free?
Yes, right. So you want to create some,
It's like a priority list almost. of,
yes. Yes. These are nice intuitions. Okay. Now, if you want to do even better than the ribbon filter, I'm just telling you that this exists. I'm also telling you that this ribbon filter is not the stuff of folklore. In fact, there's an implementation of the ribbon filter as a part of RocksDB as of 2020, which you could use and run experiments on if you like. And in fact, I will also tell you that there is another kind of variant of the XOR filter that uses a technique called spatial coupling to do even better. And what spatial coupling means is it's actually going to apply the 3 random hash functions kind of over a sliding window over the filter, which means that for every new key, you're going to slightly shift the sliding window. And this means that like now you have these new slots here that you're including in your space of choices. And that kind of increases the probability that you'll succeed while still kind of keeping everything tight together. Right? So with all these kind of techniques, you can actually begin to approach the lower bound. But these techniques take potentially a higher construction time, so you have to pay somewhere else. Okay, but this is for static filters, so maybe construction time doesn't matter as much. We just do it once and then we're good. Okay, we're soon done. Let's just kind of conclude about the performance properties of the XOR filter. Construction time, I've told you conceptually how construction works. I haven't actually told you how the nitty-gritty of construction works, but I guess you will just have to take my word that you can do this in linear time. The cost for a positive query and for a negative query, both, we have to compute 3 hash functions and potentially incur 3 cache misses. So this is going to be significantly slower than a Bloom filter, right? Significantly slower, but hopefully a lot more memory efficient. Okay, yep. So basically, we've seen that there's this whole spectrum for static filter data structures, right? If we get closer to the block Bloom, we're faster. And as we move towards XOR and we're more careful about space, we get a lower FBR, right? And and you can use whichever filter you want, depending on the application that you're running. Okay, thanks very much. That's all for today.